Welcome back to the series of lectures on high-performance scientific computing. We have been discussing directive-based programming for GPGPUs and multi-core systems using OpenACC. In today's video, we will see a little bit more about these directive-based programming languages. One of the main things that we have to look at when we are using directive-based programming is loop optimization. If you look at majority of the scientific programs, most of the time is being spent in loops. Obviously, every loop can execute in very different ways. So, using OpenACC loop optimization, we can speed up some of the most time-consuming portions of the code which are spent in these large loops. Here is a simple example of matrix multiplication. Here you will see a nested loop of 3 dimensions. The matrix themselves are 2-dimensional, but if you look at the loop indexing, it has to become 3-dimensional because of the nature of the mathematics of matrix multiplication. You have 3 loops going from I, j and k, where Cij is now being summed up over the product of Aik into bkj. Now, if you look at this code, this will allow different levels and different types of parallelism, and we'll see how this works with our loop clauses. So, today we will discuss basically parallelizing loops. One of the first clauses that we will use is called the auto clause. The auto clause gives control to the compiler, and it tells the compiler to decide which loop is parallelizable or not. This clause is really useful if you are unsure about the mathematics underneath the code and you do not know which loop is safe to parallelize or which loop is unsafe to parallelize because of certain data dependencies. The compiler in this case will analyze the code and make its decision whether a loop is parallelizable or not. So, for example, if you were to use the auto clause for the matrix multiplication program, you will implement it in this manner. You can use the auto clause using the kernel's directive, but when you use it using the kernel's directive, the auto clause is already implied. That means if you choose to use the kernel's directive instead of the parallels directive, you do not require to use the auto clause. Here the compiler takes the heavy work of deciding whether the loop is parallelizable or there are any other data dependencies. But if you are using the parallel directive, then the auto clause can become very useful because then the responsibility of the safeness of the program resides with the programmer. So, if you are using the kernel's clause, please do not use the auto clause. The next clause that we will discuss is the independent clause. So, the independent clause basically says that this loop is parallelizable. This will overwrite any decision that is taken by the compiler about the loop. Here, the control is now given to the programmer. So, adding an independent clause will force the compiler to parallelize even a non-parallelizable loop, even if there are data dependencies. So, it essentially gives more power to the programmer, but that means the programmer has to be careful where he or she uses the independent clause. When you use the parallel directive, the independent clause automatically becomes implied, because with the parallel directive, the programmer is determining which loops are parallelizable, and thus the independent clause is not needed. Ensuring loop correctness is very important for the accuracy of programs. Now, you also have the sequential clause, which is SEQ. So, this forces the compiler to run a loop sequentially. So, especially this is very important if you have determined that you have a loop where there is a certain data dependence. So in this sample code of matrix multiplication, you can see that the outer loops of I and j can be parallelized, whereas the innermost loop, which runs over k, has to be run sequentially. So we can now implement it by suggesting to the compiler that the outermost loop are parallels, whereas the innermost loop is sequential. So the compiler sometimes may automatically apply the sequential clause to loops that do not have too much dimensions as well. The other clauses that are important are private and first private clauses. The private clause allows the programmer to define a list of variables that are thread private. That means each of the threads will have its own personal copy. And this is given by a list of variables using comma separation. The first private is exactly like private, but the private values are initialized to the same value as that of the host. If you use a private clause, while each of the threads have their own copies of the variables, they are not initialized to the value and remain uninitialized. Whereas first private will initialize the values of these private variables to the same value of that of the host. So the variables private and first private are private to the loop level on which the clause appears. So remember, we can give the directive at different loop levels. So at whatever loop level you are giving the private or the first private clause, that's where the variables will become private or first private. Private variables on an outer loop can be shared within an inner loop, or rather are shared within inner loops. So in this example, you have two loops I and j. So in this, you have private copies of the variable temp. Each thread will have its own copy of temp when it is being parallelized over I. But when further threads are being spawned and the threads are parallelized over the loop j, the variable temp is no longer private. It is actually shared. So one has to be aware of these intricacies. So by default, scalars are first private when used in a parallel region and private when used in a kernel region. Except in some cases, scalars do not need to be added to a private clause. These cases may include, but are not limited to, scalars with global storage, such as global variables in C, module variables in Fortran. When the scalar is passed by reference to a device subroutine, when the scalar is used as an R value after a compute region like a live out. Now, please note that putting scalars in a private clause might actually sort of hurt performance. Looking at further loop optimizations. Now, if you have a nested loop, we can also use the collapse clause. And we can also say how many nested loops we would like to collapse. For example, again, in the matrix multiplication problem, you can collapse the I and j loops, but the k loop is being run as a reduction operation. So essentially, you can turn a multi-dimensional loop nest into a single dimensional loop. This is very, very useful for increasing memory locality as well creating larger loops to expose more parallelism. So here you can see that we are collapsing the two loops I and j. So essentially what happens is that when you're doing the matrix multiplication, or rather when you're doing to the loops of I and j going from 0, 0 to 3, 3, you are now taking this loop, which is loop across I and j, and collapsing it, and so that this loop is now run in some sort of a sequential sense where you would go from 0, 0, 0, 1, 0, 2, so on and so forth till 3, 3. So this becomes a large single loop. This has significant advantages when it comes to memory locality. The other way you can implement this is something called as a tile clause. The tile clause essentially breaks the multidimensional loops into tiles or blocks, and this is very useful to increase data locality. it will be able to execute multiple tiles simultaneously. Again, going back to the example of the matrix multiplication, here we say ACC kernels loop tile 32, 32, and essentially what's going to happen is that it's going to take these 3 loops and break it up into tiles. So what's going to happen? If I take the tile clause here, let's assume that we are doing a 4 by 4 tile. If you say I want to tile it 2 by 2 for these 2 loops, not 3 nested loops in this case, what essentially is going to happen is that the compiler will break it up into 4 tiles, each will do one of the colored regions. Next, you have gang, workers and vectors. Gang, workers and vectors define the various levels of parallelism we can achieve in OpenACC. The parallelism is most useful when you're parallelizing multi-dimensional loop nests. OpenACC will allow us to define a generic gang worker vector model that will be applicable to a variety of hardware, but we will focus on GPU specific implementation. For example, looking at this image, you typically have a multi-dimensional work package. So you have the entire gang which works on the entire 2 by 2 or 3 by 2 or n by n matrix. A vector can be assigned to a single row or a single column, and then you have a series of vectors working together as workers, and this whole package is known as a gang. So when we are parallelizing our loops, the highest level of parallelism is at the gang level, when you have an entire group going in together. So typically when you're encountering either kernels or the parallel directive, multiple gangs will be generated and loop iterations will be spread across these gangs. These gangs are completely independent of each other, and there is no way for the programmer to know exactly how many gangs are running at a given time, which ones are running simultaneously, which one is running in which order. So all the gangs are truly parallel. In many architectures, the gangs have complete separate or even private memory. So how the memory organization takes place for gang is also dependent on the architecture that you're running on. So in the code example, we will see that we are applying to the gang clause to the outermost loop. This means that the outer loop iterations will be split across some number of gangs. These gangs then execute in parallel with each other. Whenever a parallel compute region is encountered, some number of gangs will be created. The programmer is able to specify exactly how many gangs to create. A vector is the lowest level of parallelism. Every gang will at least have one vector. A vector has the ability to run a single instruction on multiple data elements. For example, when you expand out the loop, one vector will work on multiple data indices. Different architectures can implement vectors in different ways. But the beauty about using OpenACC is that it allows us to define them in a general non-hardware specific way, so that when you take the code from one particular hardware, let's say you're taking it from a multi-core CPU to another GPU, it will make its modifications as per needed. There's no need for the programmer to go to lower levels of programming to specify this. For example, in this case, when you have a nested loop, you will create a gang of workers on the loop I, but then you will create vectors on loop j. The worker clause is a way for the programmer to have multiple vectors within a gang. The primary use of the worker clause is to split up one large vector into multiple smaller vectors. This is very useful when our inner parallel loops are very small and will not benefit from having a large vector. Remember that if your workload is very small, it's not useful to parallelize because the overheads of parallelization then become too prohibitive and any benefits of parallelism is then lost. So if you have small workloads, which typically is in the innermost loops, it is better to run them serially. In our sample code over here, we are going to apply both the gang and worker level parallelism to the outer loops. The difference in this is that this creates for our code, we can have small vectors running inside the inner loop. This will most likely improve the performance if the inner loop is relatively small. If the inner loop is large, then probably it will not give us better performance. So if you look at the parallel directive syntax, you'll have to then specify what the number of gangs are, what is the number of workers, and what is the vector length. So in this particular code, we are saying that we have 2 gangs, we have 2 vectors, and the vector length is 32. You may also define where they belong in the loops using the gang and worker vector clauses. So for example, here you say the outer loop which is looping over X has gangs and workers, and the inner loop Y is composed of vectors. You can also apply the gang worker vector clause when you're using the parallel loop construct. You can say you have 2 gangs, 2 workers, and then again a vector length of 2 in this example. If you're using the kernel directive, then you can say gangs and workers, and then inside, when you're doing the loop, you can specify what the vector length is. When using the kernel directive, this process is very simplified. So you have gang specified there, you have worker specified there, and then you have the vector which is specified below. If you do not specify any numbers, the compiler then will decide what the number should be based on the information it has. Each loop nest now can have different gangs and different workers and different vectors depending on the workload. In this case, we are giving you the same example with different numbers of gangs and workers, but you can assume that if the 2 nested loops had different workloads, you could design it specifically for your particular hardware. So here we have a simple 2-dimensional loop nest. We have specified 1 worker with a vector length of 8. We do not specify how many gangs to generate, so the compiler then will create enough gangs to cover all this loop. So here what we are saying is the vector is fixed of length 8 and you'll have 1 worker per gang. The compiler will be able to generate as many gangs as it wants. And these gangs are completely separate from each other and they are indistinguishable. We will show that these gangs apply to the physical loop diagram, but this representation might not be 100% accurate to what the compiler might decide. So if you look at the representation over here, the compiler can design it in any which way they want. The vectors are colored so that we can observe which loop iterations they are being applied to. Based on the size of the loop nest, the compiler can theoretically generate 4 gangs. So we'll say this is 1 gang, this is another gang, and another gang. If we were to choose the vector length of 4, but we have kept everything else the same, the dimension of the outer loop is still the same, but it is still being distributed across the gangs. So the number of gangs will not change. Let's observe how our code will function with the same smaller vector size. We are still generating 4 gangs, but now each vector is computing 2 loop iterations. If we wanted to generate more gangs, we should increase the size of the outer loop. So you'll have 1 vector, then another vector, then so on and so forth. So you still will have 4 gangs and creating 4 vectors. Now, if we say that we have 2 workers per gang and a vector length of 4, now let's see what happens. Since we have increased the number of workers, we will now be only generating 2 gangs. So you'll have 2 workers, vector length of 4, and this is how the program will proceed. Now, let's look at a situation where the gang worker vector model is very useful. We have reduced the size of our inner loop to 4 iterations. Let's try to run this loop with a vector length of 8. So, this gang will create this vector. This gang will work on this vector. So, we can see our vector length is much larger than our inner loop. We are wasting half of our vector, meaning our code is performing half as well it should. So, it is doing a lot of redundant, useless calculations. Now, in this case, we can fix this by breaking up our vector among 2 workers. Instead of having one long vector, we have 2 shorter vectors. This setup will fit our organization of our loop better. So, now you can create a gang with 2 workers with work on these 4 vectors and another gang which will work on these vectors. So, we are no longer wasting a portion of our vectors since the smaller vector size now fits in our loop properly. We always need to consider the size of the loop when we are choosing the gang worker dimensions. Now, this is specific to your problem. Here is an example where we are going to use the collapse clause as well. So, we have a nested loop with a collapse clause for collapsing the next 2 loops. So, we look at the same matrix problem and we have now collapsed it. We have collapsed the innermost loop. This is going to be one gang and then you have another gang. Collapse clause now allows us to combine 2 small loops into a large one. This exposes additional parallelism, allows us to use a longer vector. Now, let us see what are warps. So far, we have been using a very small number of gangs, workers and vectors simply because they are easy to understand. When you are actually programming, the number of gangs, vectors and workers will be much larger. When you are specifically programming for an NVIDIA GPU, you will always want to have your vectors large enough to fully utilize warps. A warp, simply put, is an optimized group of 32 threads. To utilize warps in OpenACC, make sure that your vector length is always a multiple of 32. So, if you say use the device type clause, so it will give information to the compiler about what type of device you are running on. This allows you to optimize for one type of GPU without hurting the performance on another CPU. Multiple devices can then be specified on a single directive. So, here are some rules of thumbs for loop optimization. It is not a great idea to set the number of gangs in your code, let the compiler decide. Most of the time you can effectively tune a loop nest by adjusting only the vector length. It is very rare to use a worker loop. When the vector length is very short, a worker loop can increase the parallelism in your gang. When possible, the vector loop should step through your arrays. Use the device type clause to ensure that the tuning for one architecture doesn't negatively affect other architectures. So, the key concepts today we have discussed are the loop directive enables the programmer to give more information to the compiler about specific loops. This information may be used for correctness or to improve performance. The device type clause allows the programmer to optimize for one device type without hurting the others. Thank you.